Hi, this video is part of a machine learning course developed by professors from Unesp and Unicamp with a particular approach, the focus on robotics domain. We will cover the main topics of a machine learning course that of course can be applied to a number of problems in all fields of knowledge, but here we will direct the application of the contents to the problems that are typical in robotics nowadays. There's a number of practical tasks where the traditional approach, the traditional programming of computers is virtually impossible. Many of these tasks are basic requirements of modern robots, like for example interaction between robots and humans, locomotion of robots with distinct architectures in different and complex environments, the ability to recognize objects in the environment, and so on. In this kind of task, learning is the key to make these applications possible. We expect that these lectures can help you to understand the key concepts and implications of machine learning. However, it's important to remark that they are only a part of the methodology. It's important that the student can follow all steps of the course to ensure a full understanding of the field. In today's video, we will try to explain what is machine learning, the history of this field, and how does this area relate to other fields of knowledge. Also, when we say machine learning, we are talking about a large set of learning types and methodologies. In this lecture, we will introduce and organize these fields that will be further discussed in the course. Let's start.
Let's consider a timeline of machine learning. We can start our timeline in 1936, when Alan Turing proposed a Turing machine. And what is a Turing machine? We can understand a Turing machine as a mathematical model of an abstract machine that could manipulate symbols. This was the theoretical foundation that allowed the modern computers possible. The first electronic programmable computer built was the ENIAC. It has about 50 tons and it was built between 1943 and 1946 at the University of Pennsylvania, USA. The first work recognized as an artificial intelligence work was a paper named A Logical Calculus of the Ideas Immanent in Nervous Activity. This paper was published in 1943 by the neurophysiologist Warren McCulloch and the mathematician Walter Pitts. They investigated biological neurons and they created a mathematical model of neurons. The work of McCulloch and Pitts inaugurated what would later be known as the field of AI called artificial neural networks. In 1949, Donald Olding Hebb, a psychologist, studied the neural basis of learning. He published a book called Organization of Behavior. He proposed that the learning in neurons could be expressed through a very simple rule. His learning law was called Hebbian learning. In 1952, the IBM researcher Arthur Lee Samuel created the first learning program for a game. His program became a better player after each game. It was able to observe the best moves, and with this information it was able to improve its strategy. Arthur Samuel coined the term machine learning. The field of AI was officially born at a workshop in 1956 at Dartmouth College, USA. Names like Marvin Minsky, Claude Shannon, John McCarthy, and others were part of the team that started this new research field. The new field was soon divided into a number of research branches. John McCarthy was the one who coined the term artificial intelligence. In about 1957, Frank Rosenblatt proposed the perceptron. The perceptron was an electronic device constructed based on neural principles that has the ability to learn. In fact, Rosenblatt extended the neuron of McCulloch and Pitts to a model that was able to assume continuous values. He also formalized a training law to the perceptron. However, Rosenblatt was not able to extend his training law to complex artificial neural networks. The limitations of the learning in perceptrons remained for decades. It was only due to the work of Paul Werbos in 1974 and Hummelhart, Hinton and Williams in 1986 that the training of networks with multiple layers was possible. The result of their work was the backpropagation algorithm, the most powerful algorithm so on. Learning became very popular in AI and the number of uses of AI in practical situations increased day by day. The term deep learning was introduced to the machine learning community by Hina Dester in 1986 and to the artificial neural networks community by Igor Eisenberg and colleagues in 2000. Deep learning uses multiple layers of nonlinear units to proceed features extraction and transformations. Each successive layer uses the output from the previous layer as inputs. These multiple layers work as multiple levels of abstraction in a network and allows the organization of concepts hierarchically. According to The Economist, data is the most valuable resource available on Earth today. Data is even more valuable than oil. In fact, the most valuable companies around the world today are companies that work with data. In this graph, we can see the applications of machine learning in business. In one axis, we can see the benefits of these technologies to the companies, from low to high, and in the other axis, we can see the complexity of these developments from low to high. In the region with high benefits to companies and with relatively low complexity, there are tasks like face recognition, chatbot and assistants, products recommendation based on consumer profile, risk management, analysis of consumer behavior, and so on. In the region of high benefits and high complexity, that we can consider like the focus of the machine learning developments in next years, we can find the image and video recognition, voice authentication, new product development, and so on. The ability to learn and make correct decisions based on data is extremely valuable. But what exactly is machine learning? We will present here the definition of machine learning according to some of the specialists in this field. Arthur Samuel defines machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. In fact, Arthur's algorithm was able to use strategies that he did not program. Simon defines machine learning as adapting the system such that it can perform the same task or the task in the same population more efficiently next time. This definition emphasizes the training of a learning system. A learning system is not expected to know everything from the beginning, but it tends to become more and more efficient with time. Murphy says that machine learning is a set of methods that can automatically detect patterns in data and then use the uncovered patterns to predict future data or to perform other kinds of decision-making under uncertainty. This definition emphasizes that there are at least two types of data in machine learning: the data that will be used by the system to learn and the data that will be presented to the system after his training. A well-trained system is able to predict or to classify data it did not necessarily see during his training. Alpedin defines machine learning as programming computers to optimize a performance criterion using example data or past experience. If we are presenting some training data to a learning system, how can we say that the learn can be finished? That is, how can we say that we can stop training because the system has already learned as well as possible? This definition suggests that we must have some performance criterion to evaluate learning during the training process. Marsland defines machine learning as making computers modify or adapt their actions, whether these actions are making predictions or controlling a robot, so that these actions get more accurate, where accuracy is measured by how well the chosen actions reflect the correct ones. Sometimes the output of a learning system can be a prediction of a time series, for example. In other systems, the output can be a class to which some input belongs. In robotics, it is usual that the outputs can be actions that the robot should perform. If a robot decides to run and stomp with a wall, for example, surely this is an indication that the training was not effective because the chosen action was not the best one. It does not matter what kind of output we have. A well-trained system will be more accurate with time. Jaron defines machine learning as the science and art of programming computers so they can learn from data. When he compares machine learning to an art, he synthesizes the level of difficulty we often face in machine learning. A particularly useful definition of machine learning is the one from Tom Mitchell. According to Mitchell, machine learning is the field concerned with the question of how to construct the computer programs that automatically improve with experience. Formally, a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at tasks in T as measured by P improves with experience E. How exactly does machine learning relate to artificial intelligence? Let's consider the set of all possible AI systems. Those related to speech recognition, image recognition, expert systems, and so on. We can understand machine learning as a subset of these systems. Machine learning is related only to those systems that improve with experience. In traditional programming approach, someone must write a code that will be responsible for transforming some input data into some output data. If for some reason you're not happy with your output data, your only choice is to rewrite your code, that is, to adapt your code so that it can correctly map your input data into your desired output data. It is important to remark that this requires the programmer to know exactly how to map all the input data into the output data. This is not the same approach that we have in machine learning. Let's consider our learning system. The first thing our learning system requires is some training data. Suppose that we have examples of real fruits, apples, oranges, pineapples, whatever. The first thing that we need to do is to extract from these fruits some relevant features. For example, height, width, weight, predominant color, shape, position of leaves, and so on. Sometimes we can have a stage where these parameters are treated and organized according to some criteria. Finally, some of these features can be selected to provide us some training data. Now, our learning system needs something else. A learning algorithm that will tell it what to do with this data, or, in other words, how to learn. Now we have a training phase, where this learning algorithm is running over the training data. After the training phase is done, the system is ready to use. Now, for example, we can present the system some data that is not exactly the same data present in our training samples. A well-trained system is able to correctly classify examples close to those in the training set. This property we call generalization. Our system can also predict points in series that were not present in the training set. Note that no one told the system how to transform the input data into the output data. The system has learned by itself how to do that, even for cases that it was not explicitly trained for. When we say machine learning, we are talking about a lot of different types of learning. We can classify the types of learning in many different ways. According to the nature of the input-output relation, we have the supervised learning, the unsupervised learning, the semi-supervised learning, and the reinforcement learning. According to the data model relation, we have the inductive learning and the deductive learning. Besides these, we have a large number of algorithms that are based on distinct fundamental principles. We can mention the evolutionary learning, the deep learning, the deep reinforcement learning. In unsupervised learning, learning has no teacher. This means that learning algorithms try to identify relations between data with no additional information. In other words, examples in training set have no labels or targets. The capital X represents the training set. X is a training example, and in the training set there are n different training examples. Each training example can have d dimensions. These dimensions are also called attributes or features. Here we have a training set with 18 different examples in 2 different dimensions. In supervised learning, the learning has a teacher, that is, someone that assigns the correct labels to the training examples. The examples in training set have correct responses, targets, or labels. In other words, someone will tell us that these examples belongs to a class of apples. These examples belongs to a class of oranges, and so on. The capital X represents the training set. X is a training example. Now, to each training example there is assigned a target T that relates the training example to one of the classes of the problem. Also, in the training set, there are n training examples. Each training example can have d dimensions, attributes or features. Here we have a training set with 12 examples in 2 dimensions. Each example is necessarily assigned to one of the 2 classes available. Semi-supervised learning is a framework of algorithms proposed to improve the performance of supervised algorithms through the use of both labeled and unlabeled data. Reinforcement learning is a learning process based on trial and error. The learning system chooses actions and receives feedbacks from the environment. These feedbacks can be rewards or punishments, and these feedbacks tells to the agent how good is the system performance. So there is no training set. Since robots are entities that usually interact with the environment, this is a particularly interesting paradigm to adopt in robotics domain. In evolutionary learning, the learning process is inspired on the evolution of biological organisms. The learning system has internal models of a population that successively generates descendants with some mutations in order to stimulate the development of individuals with better chance to achieve a successful performance in the environment. There is no training set. Other type of learning is the inductive learning. In inductive learning, system obtains new knowledge or refines its model or its concepts based on specific information or data that is arriving. If a new data arrives, this can change the knowledge of the system. In a deductive learning system, the system obtains new knowledge or refines its model or concepts, typically using logic. You can observe that there is no training data arriving here. The knowledge is not new, it was implicit in the initial knowledge of the system. Deep learning is a learning approach that enables the computer to learn complicated concepts by organizing them hierarchically, in a way that, if we draw a graph showing how these concepts are built on top of each other, the graph is deep, with many layers. Deep reinforcement learning is a method based on deep learning technique that extends the traditional reinforcement learning to the entire process from sensors to motors.